Thanks. So I'd like to thank the organizers for the invitation to speak here. I should mention that my talk is probably one of the few outliers in this workshop in the sense that it has nothing to do with complexity, although there might be some downstream connections. Okay, so this is based on joint work with a number of people whom I will mention the relevant papers as we go along, but those people include Adam Marcus, Prasad Tetali, Jiange Li, J.O. Wu, Lia Wang, and Yanis Kontoyanis. So just to outline the talk, I'll start out with some background and motivations for thinking about the connections between entropy inequalities and additive combinatorics. And then I'll discuss one basic question which we can actually treat in considerable generality, so in the general setting of locally compact abelian groups. And that's the question of how the entropy of a sum of two independent random variables is related to the difference. I mean, the entropy of the difference. And then, that's really an example question. There are many other things that can be said, but this is one question that we will isolate in order to, make the exposition reasonable. But then we will look at phenomena that arise for particular groups. And although I mentioned three settings here, Rn, the integers, and Z mod Pz, I will focus only on the integers today. So some broad motivation. I don't think I need to introduce additive combinatorics for people here. I'm sure people have seen it in some avatar or the other. But for instance, results like Semireddi's theorem, which guarantees the existence of arithmetic progressions of arbitrary length for subsets of the integers that have positive upper density and so on, are classical results in additive combinatorics. And generally speaking, additive combinatorics has to do with looking not just, if you look at the origins of additive combinatorics, it probably comes from number theory, but questions where it was not just questions involving the multiplicative structure, so prime factorization, for instance, but additive structure, things like arithmetic progressions and so on. But from those origins, one can ask questions about additive structure and more general groups, not necessarily the integers. And now there is a rich theory that has been developed. The book of Tao and Wu, for example, consolidates a lot of this theory with applications to many different areas. But in any case, one of the sets of tools that are very useful in additive combinatorics are so-called sumset inequalities. So what are these? When we talk about a sumset, this is really just the Minkowski sum. If you take two sets A and B, and you have a group operation, so A and B are subsets of some group, and you have a group operation plus, then A plus B is the set of all pairwise sums that you get by taking elements from A and elements from B. Okay, so a sumset inequality is some inequality that relates the cardinalities of various sumsets. So for example, here are some classical sumset inequalities developed by Pluneke and Rusha, for example. So Rusha's triangle inequality relates the cardinality of the difference set A minus C to the difference sets A minus B, B minus C, and the set B. So the difference set is defined in exactly the same way as the sum set, right? So A minus C is just the set of little a minus little c, where little a is in capital A and little c is in capital C, and so on. And then there is the sum difference inequality, which relates the cardinality of the sum of two sets to the cardinality of difference of two sets. Okay, so these kinds of inequalities, you can ask if they hold for finite subsets of any group. And so for example, these turn out to be facts for finite subsets of the integers. Okay. But these kinds of inequalities, so sumset inequalities of this type are often not sharp, and they hold in considerable generality. But you can also look for sharp inequalities. So, for example, the Cauchy-Davenport inequality. Actually, I'm cheating. The Cauchy-Davenport inequality is this statement for Z mod Pz. But let's just look at the integers. Says that if you have finite subsets of the integers, then the cardinality of the sum set is at least the sum of the cardinalities minus 1, with equality if and only if the two sets are arithmetic progressions. So this is actually very easy to see, right? Because if you have two subsets of the integers, the nice thing about the integers is that it's an ordered set. So if you have a set, so first of all, cardinality is not affected by translation, right? So you can translate both the sets A and B to start at 0, for instance. And then you have a bunch of elements of A starting at 0 and another bunch of elements of B. And if you just look at, let's say, the smallest, you order these, and then you look at, let's say, A0 plus all the elements of B, and then you look at the largest element of B, whatever that is, plus the other elements of A, you end up with a set that is ordered of cardinality mod A plus mod B minus 1. So this is really an elementary observation.
Don't you need the common difference to be the same?
Sorry? Yes. Yeah. Here, for equality, you need the common difference to be the same. Thank you. Yeah. Okay. So but one can ask about stability of these kinds of inequalities. So, for example, suppose you know that the size of A plus A. So what this tells you is that the size of A plus A, which, by the way, is not the same as 2A, right? It's not just it's not just every element of A multiplied by 2, because you can have distinct elements being added. So if the size of A plus A is not too large relative to the size of A, right? So let's say it's bounded by some factor k times the size of A, then Feynman's theorem, for instance, guarantees that A is close in some sense to some generalized version of an arithmetic progression, right? So this is a very, very powerful theorem which has many applications, including to random matrices and many other areas. But in any case, so that's some of the classical theory. But what's the connection with entropy? Well, there's a connection between cardinalities and entropy, which is long known. So, for instance, and has been used in combinatorics for a long time. So, for instance, if we denote by capital H the Shannon entropy in the discrete setting, then we know that the entropy of the uniform distribution on a finite set is just the log of the cardinality of that set. And this connection has been used quite a bit. So probably starting with Shearer's lemma, and then Jayakumar's proof of Bregman's theorem, and then many other ways in which entropy has been used for counting problems, for example, by Jeff Kahn and Ehud Friedgut and others. So in any case, a few years ago, Imre Ruscha, suggested that perhaps some of these entropy inequalities would also be useful in additive combinatorics, and he proved some results and formulated some conjectures, and subsequently there's been a bunch of work. So in particular, in the sort of direct inequalities, possibly loose that I mentioned, so this paper of Ruscha, paper with Adam Marcus and Prasad Tetali are papers of that type. And then if you want to look for sharp inequalities, then a paper of Jog and Anantaram, or this paper of Tao, and a paper with Wang and Wu treat those kinds of inequalities. So what's our goal? So our goal is to continue this development of an entropy theory in additive combinatorics, and we want to focus both on phenomena that are independent of the group you are looking at, and on phenomena which care about the group. So there are many motivations for this. So our original motivation actually came from probability. So it turns out that these kinds of inequalities, entropy inequalities, are related to basic questions in probability, like the rate of convergence in the entropic central limit theorem, which I won't have time to get further into that connection. But also there's applications to additive combinatorics, to convex geometry, to information theory. So in particular, some of these inequalities have been used by Wu, Shamai, and Verdu to improve our understanding of the degrees of freedom of the interference channel and so on. This is a classical communication problem. So anyway, let me jump into it with just a little bit about notation. So the discrete entropy is something that is familiar to everyone here. We've been talking about it all week, but there's also a notion of continuous entropy. So if you look at a random variable x, which has some density little f on Rn, then you can talk about the differential entropy, which is just minus the integral of f log f. And this is, of course, just the analog of the discrete entropy if you replace the sum by an integral and probability mass function by a density function. But now things change a lot because this entropy need not be non-negative anymore and so on. But in any case, you can also talk about relative entropy, and that's always non-negative, so that still gives you some, some nice properties. But in any case, what I want to just mention without spending too much time on this is that one can use the following unified setting. So as long as one has a locally compact group, then you're guaranteed a Haar measure, which is a translation invariant measure. And as long as you define the entropy as minus the integral of f log f, where you look at densities with respect to the Haar measure, this captures both the discrete entropy for example, for the integers or whatever, and the differential entropy, and it generalizes it to general locally compact groups. And so I mean, I just want to say that to make the point that some of these results can be stated in the general setting of locally compact abelian groups, and then we are measuring the entropy with respect to this Haar measure on the group. So, but it's for all practical purposes, if you focus on the integers and the real line, that's sufficient for now. Okay, so here is one basic question. So suppose y and y prime are IID random variables taking values in some group G, and when I say density f, you can replace that by probability mass function if you are thinking about the discrete setting. So then the question is just this: how different can the entropy of y plus y prime and the entropy of y minus y prime be? Okay, this seems like a pretty fundamental question, right? You add two independent random variables or you take the difference. How different can the entropies be? Well, of course, if y has a symmetric distribution in the sense that its mass function or density is symmetric about the identity in the group, then y plus y prime has the same distribution as y minus y prime, and the entropies are not different. So this is really capturing something about how asymmetric a probability distribution on a group can be. And so here is one answer. If you take G being either the group of the integers or the group of the real numbers, the entropies of the sum and difference can differ by an arbitrarily large amount. Okay? So in other words, given any m positive, there exist IID random variables, y and y prime, of finite entropy, such that the difference between the entropy of the difference and the entropy of the sum is greater than m. And this goes both ways. So one way is due to Lapidot and Peat, and the other way is due to Emmanuel Abe, Jiange Li, and us. So
answer 1 and answer 1 prime, totally different proofs, say totally different ideas.
Yeah. Okay. So I'll mention that in a minute. So yeah. I mean, one can prove them in a somewhat unified way, but there is a difference between them, and the difference between them is because a priori you do not expect. It is not even clear if there should exist random variables such that the entropy of the sum should be greater than the entropy of the difference. In general, you would, so even for sets, for example, it was not known until the 60s whether there is a subset of the integers such that the size of the sum set is bigger than the size of the difference set. This was a combinatorial question which was solved by Conway. He came up with the first examples of so-called more sums than differences sets. Okay, because the thing is, if you look at differences, right, it's throwing out points on both sides because the difference set is symmetric, right? The sum set is not, and so in general you might expect the size of a minus a to be bigger, but yeah, it turns out it's not always bigger, although they're much rarer to find. Okay. But in any case, it turns out that so that's why I bothered to stress the fact that we have two answers here. But in any case, yeah, I mean there is a way that you can sort of prove these in at least by a unified proof strategy. But perhaps the easiest way to prove this doesn't work for this, which might be more challenging because this is saying that the entropy of the sum can be arbitrarily larger. Right.
So is there a connection between the discrete solutions and this?
Yes. So the idea here is to first do it for the integers, and then you can use some approximation arguments to do it for the real line.
Why can't you replace y prime with minus y prime to go from one to the first one? They are IID.
No, they're IID, right? So.
They can't be symmetric. This is what you explained before.
Yes.
Also, so if you prove for m equals 1, is that the hard case?
No, because for example, on the integers, you don't have a nice scaling, right? On the real line, you can do that. On the real line, if you have scaling, right? If you look at the entropy of A times a random variable, some scalar times a random variable, that's actually entropy of the random variable plus log A. So you have a scaling which can allow you to change the entropy, but in the discrete case, you can't do that, right? So.
Don't scale, right? Differences
And exactly, and differences won't scale anyway, because once you look at the difference between these two entropies, the scaling won't matter anyway. This is an affine invariant.
So,
yes.
I mean, if you look at the pair, h of sum, comma, h of difference,
Uh-huh.
can you do everything?
What do you mean by do everything?
Can you realize everything?
I mean, okay, so there are, okay, I'm not sure actually about the answer to this question, but well, you definitely can't realize everything because there are going to be some natural constraints just coming from elementary entropy inequalities, right? Entropy of the sum and the difference, the joint entropy in the discrete setting, for instance, is going to be bounded by the entropy of y and y prime, just by the data processing inequality, if you like.
We don't mention them. We are just looking at the entropy of the sum and comma.
Okay. Yeah. So then yeah. Then sure. If you are just saying is any point in the plane achievable as for some distribution? Yes. The answer is yes. Yeah. Okay. So anyway, so for example, so this is. You know, the fact that we can do this for the integers is not so obvious because, for example, if you look at z mod 3z, we can prove that the entropy of the difference is always bigger than the entropy of the sum. Okay? So, any distribution.
You don't have this.
Z mod 3z is simple, right? Yeah. Yeah. Well, this is already non-trivial to prove. I mean, it's an exercise to prove this. You know, but anyway, you can prove this. And we don't know what the answer is, for example, for z mod 4z or z mod 5z, right? We believe that there is some threshold such that, you know, for example, we know that once you go to z mod 29z, right, which is what you would need to be able to use this integer example in a finite cyclic group, you would need z mod 29z. Once you go to z mod 29z, there exists random variables such that the entropy of the sum can be bigger than the entropy of the difference. But in between z mod 3z and z mod 29z, we don't know, right? So anyway, okay, so here's the second answer though, which might, which complements the first answer. Yes?
Can you keep the point very close to the x-axis and very far away? Because answering Nathi's question, because entropy of x minus x prime is at least as like the entropy path is at least entropy one of the variables.
Yeah. Okay. So for discrete random variables, you can achieve any point in the positive quadrant. For continuous random variables, you have other things that come into play. Yes. Okay. Right. So here's the second answer to the same question. So again, we are asking how different can the entropy of y plus y prime and entropy of y minus y prime be? Well, it turns out that if you look at these, you know, if you look at these entropies and you normalize them by subtracting off the entropy of y in the first place, then the ratio between these two quantities has to lie between half and 2. Okay. So in this sense, these two entropies cannot be too different, right? So let's interpret this result. So what this is saying is that if you look at the entropy increases for addition and subtraction, right? Entropy always increases when you add an independent random variable. Look at how much it increases for addition and for subtraction. Then our first result, the first answer is stating that the difference between these entropy increases, delta plus minus delta minus, can be arbitrarily large. But the second answer is saying that the ratio must always lie between half and 2. Okay, and one thing about this result is that this result actually holds for any locally compact abelian group, not just for the integers or the real line. So for any locally compact abelian group, we have that this result holds. So Okay, so for discrete groups, for discrete random variables, half of this result was due to independently to Rusha and Tao, and Rusha conjectured the other half, and that was proved with Marcus and Teteli. But it turns out that the discrete proofs do not necessarily generalize, immediately to the continuous setting, because in the discrete setting you have all these additional properties like non-negativity of entropy and preservation of entropy on taking bijective mappings, which completely fail when you go to the continuous setting. So you need some additional things to do this in the general locally compact abelian case, but it turns out you can do it. So okay, so how much time do I have, by the way?
Less than 5 minutes.
5 minutes, okay. Then I'm not going to say anything about the proof, but I'll try to say about the second class of results, so phenomena that arise for particular groups. So all you need to look at in this slide is the definitions of Renyi entropy. So there is this one parameter family of generalizations of entropy, right, of Shannon entropy, which is the Renyi entropies. This is what is usually called the min entropy. And then, anyway, so, but yeah, the other entropy of interest would be the Renyi entropy of order 0, which is just the log of the support size of a distribution P, right? So, okay, the reason I say this is because, all right, so, okay, so one can ask, okay, so on the real line, questions about sharp lower bounds for the entropy of a sum of independent things are very important for many reasons. This is the so-called entropy power inequality due to Shannon and Stam. And I don't have time to go into those reasons or why this inequality has this form and so on. But motivated by this, one might expect that that inequalities for the integers, for instance. So is there some discrete analog of these sharp lower bounds for the entropy of a sum? And for example, Tao proved this result, which is asymptotically sharp. If x and x prime are IID integer valued random variables, for integer valued random variables, then the entropy of x plus x prime minus the entropy of x is at least half log 2 minus something that's little o of 1 as the entropy of x goes to infinity. Okay, but this is an asymptotic result. One would like results that are non-asymptotic. So there exist such results, for example, due to Hagigat-Schwarz, Abe, and Telatar, but this result is not sharp. Okay, so one would like sharp results that are non-asymptotic, and from that point of view, so we can say something in this direction, but yeah, so maybe I'll just jump ahead. Okay, so here is one discrete analog of the entropy power inequality. So what it says is that if you look at integer valued random variables, right, x and y are integer valued, then the entropy of x plus, and these are independent, then the entropy of x plus y is at least the entropy of x plus y star. Okay, so I need to define what this x plus and y star are, but these are basically discrete kinds of rearrangements. So you look at the probability mass function of x or the probability mass function of y, and then you want to rearrange these in a way that is somehow the probability mass function is approximately symmetric and decreasing away from the origin. Okay, so there are continuous versions of this inequality, by the way, which involve spherically symmetric decreasing rearrangements of densities on Rn, but you can't quite do that on the integers, right? Because you don't want to break up masses, right? So if you don't want to break up masses, then you have multiple ways of rearranging mass on the integers. You can put the biggest mass at 0, but then the second biggest mass you have to decide whether you want to put it on +1 or -1. Okay, so whether you privilege the positive side or the negative side, you get two different notions of rearrangement. So that's where this plus comes from. But in any case, okay, there's an assumption here as well, which I have. Okay, so this inequality only holds if one of the random variables, say y, has the property that its rearrangement on the plus side is the same as the rearrangement on the minus side. So that imposes a kind of regularity property on the distribution of y, regularity assumption. But in any case, under that assumption, this inequality turns out to be true. And it so happens that this is not just true for Shannon entropy, but the same inequality is true for any entropy of arbitrary order. Okay, so as a corollary of this, again, I'm going to have to rush through this. Okay, this picture might help explain the rearrangements at least. So you have some probability mass function here. Here is the plus side rearrangement. You put the largest mass at 0, the second largest at 1, third largest -1, and so on. This is the opposite rearrangement, and then let's ignore this for now. But in any case, right. So the result that I mentioned holds true for arbitrary Renyi entropies. This is written in a different notation. I apologize. This is written, this should be x plus y if you're thinking of the random variables. But in any case, one implication of this is that you can recover, as r goes to 0, you recover something like the Cauchy-Davenport inequality, whereas for r equals 1, you have an entropy inequality, and so on. So you get a whole one-parameter family of these inequalities, which in particular recovers Cauchy-Davenport. So for the integers at least. So anyway, so it turns out. So maybe I'll just mention one more thing, which is before closing, which is that. No, let me not. Okay, so. So there's this emerging entropy theory of additive combinatorics, where some very general statements can be made for locally compact abelian groups, like the statements about sum and difference. But also, I think it would be interesting to look for other sharp inequalities that can be developed for specific groups. And although I haven't talked much about it, there are applications of this theory in various areas too. Thanks. Yes.
So doesn't the entropy of the sum and difference differ by at most a factor of 2? Because the entropy of the sum is at most twice the entropy of x, which is at most twice the entropy of the difference.
So okay, so in the discrete case, yes, you can prove that. So as a consequence, I mean, okay, so this is if you fix. Right. So in the discrete case, you can prove. I think I didn't mention this, but you can prove that this ratio actually lies between 3/4 and 4/3. Okay, but one way to prove that is to use our result. So we have this general result which works for arbitrarily locally compact abelian groups, that this difference, right, the delta plus divided by delta minus. Is between 1/2 and 2, and if you just manipulate this and use the fact that entropies are non-negative, you basically get this fact. So it's finer somehow than just that fact. Sorry.
But then not every pair is
Realizing.
Oh, you're right. Yeah. Sorry.
It would be interesting to discuss.
Yeah, sorry. No, I was misthinking. Yes. Yeah, you're right. Yeah.
Wait, what was the comment? That what's right?
Sorry?
What?
It's always right.
Don't forget.
I think that is more possible.
Yeah.
There is a ratio. It's bounded. They cannot be completely one.
Yes. Yeah, that's right.
Is it possible or no? That's also you want to find it further. Now you have an arc of 3.
No. This is not sharp. So yeah. There should be other constraints. Sorry. Yeah. The thing is, there depending on what you decide to fix and what you decide to leave free, there are many different behaviors you can get. So yeah, I'm sorry I misspoke. Yeah.
So in your inequality over there, the one that's h of y plus y prime minus h of y over.
Yes.
So that was when y and y prime are identically independent.
Yes.
Suppose they're independent but not identically distinct.
Okay, so we have results in that case, but so they're more complicated to state. So I think in that case you get something like okay.
What's the expression? What are you subtracting?
Sorry.
If y and y prime.
Yeah. Then you get results involving and all 4 entropies, right? You have entropy of x plus y, entropy of x minus y, entropy of x, and entropy of y, and then so you can prove that that there's, for example, I think if you look at, let's say, a symmetrized version, so you look at something like this. Okay, now I'm going by memory. This I might be misstating exactly what this is, but this is something like this. Okay, so and if you look at the corresponding thing for entropy of x minus y normalized in the same way, then I think what you get is factor of 3 and 1/3. Okay, in the general IID case.
But is this ratio?
But I can point you to the relevant result in our paper. Yes.
But if you go back to the expression you had there, where it's an asymmetric expression because you have h of y, the one that you have originally down.
Yeah.
Are there examples where it's unbounded?
If you don't have identical distributions, I would expect so. Yeah. I'm not sure. I haven't checked, but I would expect so. I don't see any reason for it.